Today, we will see how the MR signals are detected. The MR signals are detected by using the pulse sequences. Various pulse sequences are developed and used clinically. We will today see two representative pulse sequences, 1990 pulse sequence and inversion recovery pulse sequence. Other pulse sequences, such as spin echo pulse sequence and fast pulse sequences, will be presented in subsequent lectures. On RF pulse, flips the modulation vector to XY plane to a certain degree. So it depends on what kind of pulse is used. If we use 90-degree pulse, then the longitudinal modulation will be flipped to transverse modulation. And if we use partial angle or pulse sequence, pulse, then modulation vector will flip to a certain angle. The modulation vector back to its original vector after the pulse is turned off, aligning along the g-axis, which is a static field direction. During the recovery, a component of the modulation vector can create a magnetic flux that passes through an RF coil to the nearby. So during the recovery, a component of modulation vector can create a magnetic flux through this RF coil. This flux change generates the voltage across the coil. Faraday's law of induction can explain this phenomenon. In this process, only the transverse component of the modulation vector mxy contributes to the MR signal detected by a coil. The longitudinal component of the modulation vector, on the other hand, does not contribute to the MR signal. If you see this figure, longitudinal component does not pass through the coil. The transverse component only can pass through the RF core and make a flux. So this flux change can be detected as voltage by RF coil. And the voltage detected by coil is dependent on the flux change. Okay. So flux is defined m dot A. A is area of the coil. So the components of magnetic moment, modulation, only transverse component can pass through the coil. So give the voltage. Okay, so only transverse component of the modulation vector contribute to the MR signal. On the other hand, longitudinal components of modulation vector does not contribute to the MR signal. The modulation vector reverts to its original orientation. If we use 90-degree pulse, then longitudinal modulation convert to the transpose margination. And first is off, then margination vector reverse to its original orientation, this orientation, which is parallel to the field. The margination vector processes around the axis of the static field during the process. So during reverting to its original orientation, magnetic vector processes through the V field. Okay. So the combined motion of the margination vector flipping to the g-axis and the processing around the field is a spiral motion. So actually a magnetic vector moves in a spiral way and going back to the original direction. When the margination vector points at the coil is here, the MR signal reaches its maximum. So this, right, it gives maximum flux change. So the signal will be a positive maximum at this position. When the margination vector points away from the coil, for example, in this direction, it reaches a negative minimum value. In addition, as the margination vector advances to the g-axis, going to the g-axis, the transverse component of the margination vector reduces. So transverse components will be smaller and smaller as this margination vector moving to the v-axis. Because the MR signal is proportional to the magnitude of transverse margination component, it gets smaller and smaller over time. As a result, the magnetic resonance signal decays with time and oscillates between positive and negative values. So we can detect this kind of signals. At this position, it becomes maximum, and it's moving with spiral motion and going up, and then the transverse component of margination will become smaller and smaller. So and at this position, the minimum value here, and the time goes on, margination vector will go up to the field B. So the components of transverse components become smaller and smaller. So finally will be 0. Okay. Cool. So this kind of oscillatory signals will be detected. Also the amplitude of the oscillatory motion will be reduced by this factor. The left figure depicts the signal's behavior. The FID, pre-induction decay signal, is the name of this signal. As M0 exponential minus t over t2, the magnitude of the transverse margination decreases. It also oscillates as cosine omega 0 t. So the margination vector do the precession motion. Okay? Therefore, the signal oscillates. Here, omega 0 is the normal pulsation frequency. As a result, this FID signal can be written as follows: SDK, okay, and the oscillatory motion, this one. A pulse sequence is a sequence of pulses applied to the sample in order to obtain specific type of magnetic resonance signal. By using these pulse sequences, the MR signal difference between tissue is determined. To create the grayscale MRI pictures, these tissue-dependent MR signals are employed. So using these tissue-dependent MR signals, we can construct the grayscale MR pictures. Here, MR signals relate to the relaxation times. To achieve the largest possible difference in MR signals between tissues for more contrasted MR image, a particular pulse sequence should be used. We want well contrasted MRI image. To achieve this purpose, we use some special pulse sequence. One of image factors, T1, T2, and the proton densities. These are three image factors. So one of these image factors achieves the contrast in MR images. To increase the image contrast using a certain pulse sequence, we can select one of these three image factors. Hence, by selecting a certain pulse sequence or adjustable time parameters in that pulse sequence, we can produce T1 weighted, T2 weighted, or proton density weighted MR image that provides the highest level of contrast. The types of pulse sequences utilized to produce the most contrasted MRI pictures will be covered in this part and the sections that follow. Let's first see the 90-degree FID pulse sequence. It consists of two 90-degree pulses. The repetition time between two pulses, TR, STR. The first 90-degree pulse in this pulse sequence entirely converts the longitudinal modulation to the transverse modulation. So this first 90-degree pulse will convert all the longitudinal modulation to the transverse modulation this way. The second 90-degree pulse is applied after a certain amount of pulse repetition time, TR. The second one. The longitudinal modulation in the static field is reverting to its initial value throughout the time interval between the first and the second 90-degree pulses. The second 90-degree pulse is applied during the longitudinal modulation recovery process. So longitudinal modulation is recovering in time of TR. At that time, another 90-degree pulse is applied and we can detect the signal. Then by this 90-degree pulse, just the longitudinal magnetisation recovered thus far flips back to the transverse magnetisation on an RF pulse, RF coil detects the transverse magnetisation as voltage. The third, fourth, and subsequent pulses can be used to detect the subsequent MR signals. First and second, third, fourth, we can get the FID signals. FID signal is observed during each process of applying 90-degree force, while the magnetisation vector flips in a spiral motion to z-axis. The following is the description of the MR signal. During TR, longitudinal magnetisation is recovering, and at that moment, if we apply second 90-degree pulse, then this signal can be detected. Each processes longitudinal magnetisation shortly before the 90-degree pulse is applied to presented by M0. And the time interval between application of 90-degree pulse and the subsequent measurement is represented by TR. So 90-degree pulse and another 90 pulse, the time between these two pulses is time of repetition. This term becomes unity if we measure the signal immediately after applying the 90-degree pulse. So if we measure the signal immediately after the second 90-degree pulse, then this term will become 1. Second, the signal intensity is dependent on term if TR is short. TR is short, this term survives, so signal intensity depends on this term. When the second 90-degree pulse is activated, the recovered magnetisation is flipped to the XY plane and the signal is detected. Tissue A and B's recovered longitudinal magnetisation differs due to their differing T1 relaxation times. T1 relaxation time is different, then we have different signal intensity. Figure below depicts this. This is shorter, right? The T1 relaxation time of tissue A is shorter than that of tissue B. So in tissue A, proton recover their longitudinal magnetisation fully, but in tissue B, it's still recovering. So if we use 90-degree pulse here, then we can detect strong signal in A than that of B. So T1 relaxation time is used to achieve tissue contrast in this case. As a result, we refer to the image which is short TR as T1 weighted image. And the ratio of signal between two tissues is given by this equation. Let's see one example. A and B tissues have T1 relaxation times of 1000 and 500 milliseconds respectively. A tissue's proton density is 2 times that of B tissue. In the 90-degree pulse sequence, what is the signal ratio of SA over PSB for TR 1000 millisecond? For TR 100 millisecond, what will be the signal ratio? The signal ratio is calculated by using this equation, and the proton density ratio is given by 2. So we can put the numbers here. For TR 1000 millisecond, the ratio for signal intensity is 1.46, and for TR 100, the signal ratio is 1.05. Okay. Now let's see the inversion recovery pulse sequence. Inversion recovery pulse sequence consists of 180-degree pulse and 90-degree pulse. 180-degree pulse is applied first in the inversion recovery pulse sequence. Okay. The longitudinal magnetic vector along the field then reverses its direction and moves in the opposite direction of the static field. So, magnetic vector is here before 180 degree pulse, but after 100 degree pulse, the magnetic vector reverses its direction opposite to the field. The longitudinal magnetic vector begins to revert to its original direction after pulse is switched off. So this magnetic vector is recovering after 180 pulse. It's recovering in this way. And at this point, 90-degree pulse is applied and the signal will be detected. The magnitude of the longitudinal magnetic after the pulse has been turned off is given as this equation. So the magnitude of longitudinal magnetic after the pulse has been turned off is given as this equation. We can check whether this is correct. T equals 0 at this point. So if we put T equals 0, then we get the minus M0. So this relation can be checked. At the time of Ti, time of inversion, the second pulse of 90-degree pulse is turned on at this moment. The recovered longitudinal magnetic is flipped to the transverse magnetic, result in a FID signal. So during Ti, the magnetic vector will recover, and at this moment 90-degree pulse is applied, then this longitudinal magnetic convert to the transverse magnetic and detect it as a signal. Okay. The longitudinal magnetization along the field reverses direction in response to 190-degree pulse. The longitudinal magnetization begins to revert to its original orientation along the field after the 90-degree pulse is shut off. We explained again here in this sentence. The longitudinal magnetization reaches a 0 point during the recovery process. So that is an important point, because longitudinal magnetization reaches a 0 point. 0 point here, okay? During the recovery process. The null point is the point at which the longitudinal magnetization becomes 0. We call this null point. The signal intensity becomes 0 if we set Ti to Ti null point, because there is no longitudinal magnetization at this point, so we can get 0 intensity, there's 0 signal. So from this equation, we can find a null point, Ti. So T1 log 2 is a null point for a certain tissue. That tissue has T1 relaxation time T1. So we can suppress the signal from a certain tissue by taking advantage of null points property. So at the null points, there is no signal. If we use Ti as the null point for certain tissue, then the longitudinal magnetization of that tissue becomes 0 at the time of signal detection by 90-degree pulse. So at the null point, there's no longitudinal magnetization, so the signal will be detected 0. So no signal is observed. This process is widely used to reduce fat. Fat has null point of roughly 150 milliseconds in the 1.5 Tesla field. As a result, if we employ Ti for 150 milliseconds, the fat will not have any longitudinal magnetization to flip into the plane, and hence no signal will be generated. Because fat has relatively short T1, the term STIR stands for short Ti inversion recovery force sequence. One example. What is the T1 for eliminating signal produced by T1 equal 300 millisecond tissue? So from the formula, we can get null point 207.94 milliseconds. So there's some example for fat suppression. Next example, the T1 relaxation time of the fat in the field of 1.5 Tesla is 180 milliseconds. What is the null point Ti of the inversion recovery force sequence for the fat? So we can easily calculate. We know T1 180 milliseconds. So the null point of fat is 150 milliseconds. If time interval Ti between 190 degree and 90 degree pulses is set to 150 milliseconds, the MR signal from the fat becomes 0. Thus, the fat region becomes dark in the MR image. So some example which need calculation. What are the first and the second signal intensities in the two inversion recovery pulse sequences that follow one another? So one inversion pulse sequence and another inversion pulse sequence, successive and inversion pulse sequences are applied. And in that case, find the first signal here and the second signal here. So in this figure, at first 180 degree pulse, long-term magnetization reverses its direction and recovering. And at this moment, 90 degree pulse is applied, and this longitudinal magnetization converts to the transverse magnetization, and we can measure the signal here. This is the first signal, and then the longitudinal magnetization is recovering up to here, and due to 180 degree pulse, the direction will be reversed, and recovering at this moment 90 degree pulse is applied. Then this longitudinal magnetization will become transverse magnetization and detected as signal, the second signal, this first signal. Okay. So the question is to find this first one and the second signals. So for equation for MG, this solution, we already mentioned this equation in the first lecture. Okay, at this moment, before 180 degree pulse, longitudinal magnetization was M0, and there is no transverse magnetization, 0 at point A1, and point 2, 90 degree pulse is applied. So this 190 degree pulse causes the sign of Mg to change negative, right? So at point 2, Mg will become minus M0, and still there is no transverse magnetization at point 2. Okay. So at this moment, the longitudinal magnetization recover, right? Recover, and pass the null point and increase. So Mg3 at point 3, Mg recovers during Ti, time is Ti, right? Between 180 and 90 degree pulse, the time is Ti. So longitudinal magnetization recovers during Ti, beginning from Mg2, right here. So the Mg3 will become this equation starting from Mg2, and recovering time is Ti. So we have this equation. Okay. So that is the equation we used, and T equal Ti or Mg is Mg2. So Mg2 is minus M0. We can put this minus 0, and the t got minus ti, and then we have this value. So at point 3, the longitudinal marginalization has this value. Okay, there is no transverse marginalization at point 3. Okay, at point 4, at this moment, so after 90-degree pulse is switched off. Okay, so at this moment, 90-degree pulse is applied, right? So this 90-degree pulse causes MG3 to flip to transverse marginalization and MXY4. And this MXY4 is detected as first signal. Right? At point 4 here, 90 degree is applied, and this longitudinal marginalization convert to the transverse marginalization, and this transverse marginalization is detected as signal at point 4. That is the first signal. So we found the signal intensity of first signal. Now here, from here, longitudinal marginalization is recovering, right? Recovering time is this much, which is TR minus TI, right? So TR minus TI is time interval between 0.4 and 0.5. At 0.5, mg recovers during TR minus TI starting from mg4. Okay? So time of recovering time is TR minus TI. Starting point is mg4. We already know mg4 this is 0, right? So that's cancelled. So we have only this term. So at 0.5, there's no transverse marginalization, okay? And T2 is much smaller than TR, so the transverse marginalization disappears due to the T2 relaxation. Now at this moment, 180 pulse causes the sign of mg to flip to negative at 0.6, right? So 180 degree pulse reverse the direction of the longitudinal marginalization to negative, right? So we know the mg5. We previously obtained mg5, expression of mg5, and this will become negative, right? So that's so negative, yeah. And the transverse marginalization is still 0. At 0.7 here, since mg recovers during time of ti, that's ti, right? Starting from mg6. Okay. So we have this equation, and the mg6 is given, so we put this here, and we get the expression for mg at 0.7. And at this moment, there is no transverse margination. Now finally, at 0.8, here, 90-degree pulse is applied, then this longitudinal margination will convert to the transverse margination and detect it as a signal. So 90-degree pulse causes mg7 to flip to mxy at 0.8. So it is mg7, right? So this mx at 0.8 is detected as a second signal. So we get the expression for the second signal. So in this way, we found the first signal expression and the second signal expression. Next example. The white matter in the brain has a T1 relaxation time of 500 milliseconds. What is the white matter's null point? Null point is easily obtained, right? T1 log 2. So we can get the null point of the white matter. Next question. This is B, right? Okay. What percentage of the signal in the first inversion recovery pulse sequence will be compared to the initial longitudinal margination M0 if Ti is set 500 milliseconds? We already obtained the expression, so we can use this first signal, right? We use the first signal expression already obtained in previous example, or this one. We can get 0.26. The signal is 26% of the initial longitudinal margination. And question C. In the second inversion recovery pulse sequence, what will be the signal's percentage be in comparison to the original longitudinal margination? Also, the expression for this second signal. So there is given by this equation. So second signal. This is the first signal expression. So we can get this number. So about 67% of the original margination. Next example. The system is supplied to the partial flip angle pulses, theta 1 and theta 2, with time interval Tr. Now we use the partial angle pulse, theta 1 and theta 2. Tr is significantly longer than T2. Okay? So Tr is very larger than the T2, right? And M0 is the first longitudinal margination. M0. The T1 relaxation time is 4 times the Tr. So T1 equal 4 Tr. In cases theta 1 equal 30 degrees and theta 2 is 60 degree. In this case, find the ratio of the first FID signal to the second FID signal immediately after each pulse. So we can get the first signal here and the second signal here, right? So find the ratio between two signals. And question B, what will be the angle if the FID signal following the zeta 2 pulse is 0? So in this question, find the zeta 2 in case there's no signal here, second signal. Question C, when two FID signals are identical, in case zeta 1 equal 50 degrees, determine the angle zeta 2. Okay, so let's find the solution. So at this moment, point 1, the first longitudinal margination was m0, so at point 1, mg is 0, m0, and there is no transverse margination at point 1, so mxy1 equals 0. So at this point, due to the zeta 1 pulse, the longitudinal margination m0 is inclined toward y-axis at angle of zeta 1. Thus, the longitudinal margination and the transverse margination at point 2 can be obtained, right? So longitudinal margination is m0 cosine zeta 1 to this pulse. You can get this number, and the transverse margination is also obtained. So the signal detected at point 2 is this transverse margination, right? So the signal is 0.5 m0. Okay. Now let's see the point 3 here. At point 3, mg3 is recovering during TR, and starting from mg2, all right, mg2. So mg2 here, starting from here, mg2, and recovering during the time TR. So we can get this relation. And the mg2 as given here. So mg recovers from during TR, starting from mg2. So we have this expression, and the mg2 is given here. This one, this number. So, and also T1 equal 4 TR. We get mg3 here, this number. At this moment, there's no transverse margination. The zeta 2 pulse causes longitudinal margination mg3 to be flipped to angle zeta 2 at point 4. So here, so up to this we obtained at this moment mg1 equal m0, and at this point mx2 go 0.05 m0. This is signal intensity. Yeah. And we also obtained mg3, this one, and plus we have mg4 due to this pulse. mg4 is mg3 cosine zeta 2, so we can get this number, and mx4 is mg3 sine zeta 2. So this is detected as signal, right? So the signal at point 4 is thus 0.776 M0. So the second signal. So we can get the ratio of the two signals. Z1 and Z2 is 0.64. This is first signal. This is a second signal, so we can get this number, the ratio. Next question, what will be the angle if the FID signal following the Z2 pulse is 0? So this signal, right, at this point. So once the signal at this point is 0, then mg longitudinal modulation at point 3 should be 0, right? Then the signal will be 0. So the longitudinal modulation at point 3, mg3 should be 0 if the angle after Z2 pulse is 0. Okay? So there is no longitudinal modulation at point 3, so we can have 0 signal here. So mg3, the expression is given by this equation. So this, if we put this signal, expression 0, then we can get the angle Z1. And next question, when two FID signals are identical in case of Z1 equal 15 degree, determine the angle Z2. Okay. The first FID signal at point 2 here is we already obtained, right? I mean, the expression was already obtained. So we put the Z1 is 15 degrees, so we can get this number. The longitudinal modulation at point 2 as m0 cosine 15, so we can get this number. Right? So this mg2 recovers during TR to this at point 3, right? So at this point, mg2 is 0.966 m0, right? And this mg2 is recovering during time TR. Okay, so we can get longitudinal modulation at point 3 using this relation. So we can get number 0.97 m0. This longitudinal modulation changes to the transverse modulation by Z2 angle, Z2 pulse. So we can get xy4 at point 4 here. Okay. So the question is, when two FID signals are identical, the first signal and second signal, right? First signal was 0.26 m0, and the second signal is now 0.97 m0 sine Z2. So if we equal these two numbers, that we can get the value of Z2 as 15 degrees.